So the integrated rate law. We were looking at the relationship between rate of reaction and concentration of reactant, which is all very nice, but not always very useful. The integrated rate law is going to give us the relationship between the concentration of a reactant and time. And I think we can all see that this might be more useful. We can then use this to predict, okay, well, in 5 minutes, how much reactant is going to be left? That's a useful thing. This integrated rate law also depends on the order of the reaction. So we're going to go back to looking at a simple decomposition reaction, A going to products. So here's our rate law, right? So the rate is equal to K times A, the concentration. This is a first order reaction. So the exponent on this is an understood 1. The rate is equal to negative change in concentration of A divided by change in T, change in time, right? We talked about that as well. So then what we're doing, if the rate equals this and the rate equals that, then those two things must equal each other. So this is what's called the differential rate law. To get the integrated rate law, we have to integrate that, which involves using calculus. So if you're good with calculus, you can show yourself how that works out. Calculus is not a prerequisite for this class. You do not need to know calculus to be successful. So we're just going to skip over that part and say, ta-da, here it is. So this is the integrated rate law. We can express it this way or this way. They are equivalent. The beauty of this one is that it is in the form of a line. Remember, the equation for a line is y equals mx plus b. And here we have y equals m, the slope, x plus b. So when we graph the data, we would graph natural log of the concentration of T on the y-axis. The y-axis. And time on the x-axis. Our intercept would be the natural log of the concentration of A at the original time. So it's the original concentration, that's the intercept, natural log of that. The slope of the line is equal to the negative of the rate constant. The rate constant is positive, but the slope's negative. Any questions?
This doesn't just apply to first order. Is it to,
This is just first order.
that equation?
That equation is only for first order. There's another one for second order and another for zero. The reason that we like to do stuff like this where we can get straight lines is we get this information from data, like the table we were just looking at, where we're changing concentrations and measuring things at different times, and there's always error in our data. But in this way, we know that it should be a straight line. Pointer's gone. It should be a straight line, and so we can graph the data and use linear regression or some other statistical means to average out the errors in our data. So let's look at how we could apply that. Here we're looking at the decomposition of SO2Cl2. It forms sulfur dioxide and chlorine. So we're monitoring the concentration of that reactant at a fixed temperature as a function of time. So here's time 0, 100 seconds, etc. Here's the concentration of that reactant. We see that it's going down as we expect. And then there's the data continues over here. Show that the reaction is first order and determine the rate constant. So we want to do this graphically. So what are we going to graph? So we need to graph the equation like this, graph the data. So we're going to graph the natural log of the concentration as it's changing. That's going to be our y-axis, and time is going to be on the x-axis. Now, how the heck am I going to do that on this screen? I'm going to cheat. Ta-da! Here it is. So we graph natural log of that concentration versus time, and what do you know? It's a nice straight line. What does the straight line tell us? This is a first order reaction. If it was some other order, it would not be a straight line. How can we figure out what the rate constant is? The slope. Okay. So for this first order reaction, I'm just going to use A because that other one's too long. That's what we were graphing. The slope here is negative 0.0029. And so that's going to be opposite in sign. Yeah. So the slope equals negative kt. Sorry, slope equals negative k. So, well, I've got a place for it right down there. So k equals 0.000290. Or 2.90 times 10 to the minus 4. Does that have units? Yeah, it does. What are the units on a first order rate constant? Inverse seconds. So s to the minus 1. You're not going to be able to get that out of this equation. But you can go back and look at the rate law for a first order, like we did in the first slide we worked on today, where rate equals a constant times the concentration, and you can figure it out that way. It's important to have the unit on there, because what if this was a graph with where the time units were something other than seconds? Well, the slope would be different, right? And that would make the rate constant look different, but actually it would just have different units. Any questions? Mm-hmm.
So if that graph gave us minutes, how would we alter it?
That's a good question. So if this was in minutes instead of seconds, I believe that you would just take that slope and it would be in reciprocal minutes, and then you would just convert that to seconds. Yeah. So it'd just be a factor of 60. Any other questions? Well, do you always want to do seconds? Seconds is a base unit for the metric system, and so that is the standard. Yeah. Usually we use seconds. Okay, so use the graph and this best fitting line to predict the concentration of SO2Cl2 at 1900 seconds. So there's a couple of... Zero? No. At 1900 seconds, it won't be zero. So there's a couple of different ways we could think about this. We could say, well, let's just plug 1900 seconds into this equation and find out what y equals. So y equals negative times 1900 seconds minus 2.30. So negative 0.12329 times 1900 minus 2.3. So y equals negative 2.851. Is that our concentration? No. That is the natural log of the concentration. Right. So this is the natural log of SO2CO2, because that's what y represents. So then the concentration that we're interested in is going to be e to the negative 2.851. Zero 0.0578. What's the unit on that? Molarity. Yeah, with the natural logs and stuff, weird things happen with the units, but concentrations for all of these things are going to be measured in molarity. So we can just slap molarity on there. Any questions? Yeah. It's the inverse natural log. Yeah. E to the x. Inverse natural log. Remember that logarithms are not things that you can multiply and divide by. They're functions, like sine and cosine. And so you can do them or you can do the inverse, but you can't like cancel them out, and they have their own weird set of rules. Any other questions? Okay, another one. Cyclopropane rearranges to form propene in the gas state. The reaction is first order in cyclopropane and has a measured rate constant of 3.36 times 10 to the minus 5 per second at 720 Kelvin. If the initial cyclopropane concentration is 0.0445, did I say the right number of fours? Molar, what will the cyclopropane concentration be after 235 minutes? Does anything jump out at you that we need to be careful about? Well, 720 Kelvin, what the heck is that doing in there, and how would we use that in a calculation? And minutes, right? So this is minutes, and the rate constant here is in seconds. So we need to be careful to use the time in seconds, not in minutes. So this 720K, that is in there because a rate will be different at different temperatures. And so they're specifying the temperature, but it doesn't come into our calculations at all.
So it's just there for it's just there to be there.
It's just there to be there, yeah. It doesn't matter to us at all. But for somebody who was maybe trying to replicate this or do something real with it, they would care about that a lot. So we have a measured rate constant, K equals 3.36 times 10 to the minus 5 per second. And the initial cyclopropane concentration, I'm just going to continue calling that A. Since we only have the one reactant, we don't really have to specify. This is the initial, so this is got a 0 subscript, a 0.0445 molar. And then our time, 235 minutes. We need to convert that to seconds. So 235, times 60, right? 14,400. 14,100. I can't read. So we take those numbers, we pull them out, we write them down, we label them. You could pull this guy out too and label him as temperature, but it's not going to show up anywhere. What are we trying to find? Concentration at this time. So concentration at T equals 14,100. What equation are we going to use? The integrated rate law. This is a first order reaction, so that tells us that we're going to use this guy. So you could rearrange this by, inversing that natural log. I think that's a little bit messy. So I'm going to plug the numbers in and then do the inverse log. So negative of the rate constant times the time I ran out of room, plus the natural log of 0.0445. If you didn't become convinced of this in Chem 1A, it's really important to write down what you're doing. Okay, and so I'm trying to illustrate to you here, this is what showing your work means. Now, do you absolutely have to write that stuff down? No. But I think you really should write the equation down that you're using, write it down with the numbers put in, and then write your answer. That's not too much to ask. So negative 3.36 times 10 to the minus 5 times 14100 plus the natural log of 0.0445. And it goes on a little further, negative 3.5860. So that's in my calculator. When I do the inverse log, instead of typing that back in, I'm just going to use the value that's in my calculator. If you want some help on how to pull tricks on your calculator, I'd be happy to show you. On the TI-36X Pro, what I'm going to do is I'm going to do the E to the X button, and then I'm going to do the second button and answer, and it's going to pull that answer down with all of its digits and press enter, and I get that the concentration at that time is equal to 0.0277 molar. And I'm rounding it to 3 significant figures there because it seems reasonable. This was 3 sig figs, that was 3 sig figs. It's close enough. Any questions?
Okay, so you just took the inverse log.
Inverse log, yeah. I should have written that down. Any other questions? Make sure that you can get your calculator to do this. One of the things I like about using Doceri and writing on the screen is it slows me down, should be giving you time enough to punch things into your calculator. Make sure that it's really working for you, because calculators can be very persnickety at times. Second order. Again, with the simple decomposition, here's the rate law for the second order reaction. The rate is still equal to the negative change in concentration of the reactant divided by the change in time. So again, we can set these equal to each other, and that's the differential rate law. And we integrate it, and we end up with this guy. So we get to this from the previous slide by waving the magic wand of calculus. Here, if we plot the inverse of the concentration versus time, we get a linear graph. Here the slope is equal to the rate constant instead of the negative of the rate constant. This again is the equation for a line y equals mx plus b. Consider the reaction for the decomposition of NO2. Monitoring the NO2 concentration at fixed temperature is a function of time. Tabulate the data. Show by graphical analysis the reaction is not first order and that it is second order. Determine the rate constant for the reaction. Now, if this was a homework assignment or a lab assignment, I would expect you to use either a graphing calculator or a computer and a graphing program and do this. I would not expect you to do this by hand on a piece of graph paper. That's silly. We have technology, we're going to use it, right? So we'll just fast forward. We've made the graph. Ta-da. So here is the graph for a first order reaction, natural log of the concentration versus time. And here is what a linear regression line would give us as a straight line, but is the data fitting that straight line? No. If it was scattered randomly about that, it would be fine, but it's above and then below and then above. There's a distinct pattern here. It's not linear. So for a second order reaction, we graph the reciprocal of the concentration versus time. When we do that, we get a straight line. The equation for the line is here. So what's the rate constant? 0.255. And then what, you remember what the units are? I think it was 1 over molarity and seconds. Yeah. So here, use the graph and the best fitting line to predict the concentration at 2,000 seconds. Oops. So we could calculate y at 2,000 seconds. 0.255 times the 2,000 seconds. Plus 100. I'm going to put the units in here. So the units on the rate constant we just said were 1 over molarity, 1 over second. Right? And what would the units on this y-intercept be? Inverse molarity. Yeah. Because it's 1 over. So what's going on with the units here is the seconds are going to cancel out. And then we're going to have this inverse molarity plus inverse molarity, and it's all going to work out just fine. 0.255 times 2,000 plus 100, 610. And the units there would be inverse molarity. But y is equal to 1 over the concentration. And we want the concentration, right? So the concentration of NO2 is equal to 1 over y, 1 over 610. 0.00164 molar. Yeah.
Why wouldn't the part, the plus in that 100 over the inverse molarity, why wouldn't that be 1 over 100?
That's a good question. Why isn't this 1 over 100? Because the 100 is coming from the intercept. So that is where this line runs into 0. Now, the intercept is 1 over the initial concentration, right? So the initial concentration wasn't 100. It must have been 1/100th. Yeah, good question. Anybody else? This lecture pace may seem a little slow to you, but there's a lot of stuff to absorb, and so I want to let it percolate into your brain instead of just running off. We'll have mudslides if that happens. Yeah. So this part? Or the whole thing?
Just that part.
Okay, so I plugged the time into this equation because x does represent time. And so I end up with y. I'm getting y equals 1 over the concentration of NO2 because it's a second order reaction, and I know that the form of that equation is 1 over, is equal to, is it KT? Yeah. KT plus 1 over the concentration at 0. So this is the equation that is represented by this equation, but it's simpler to just solve for y and then figure out what to do with it, if that made any sense at all. So y equals 610. Y is equal to 1 over the concentration at the time of interest. So I rearranged this and said that NO2 then must be 1 over y, which is 1 over 610. It's always great to show your units. In something like this, if you're being careful, you don't absolutely have to show the units. I just stuck them in here to show you that they are working out. It's not magic. I couldn't do that on the logarithm one because logarithms.
Okay, sorry. So just one more time, why the 100 unit? The one over.
Okay, so what I'm doing here is I am using this equation. Okay, this equation comes from this line. So I'm just trying to find where on this, at 2,000 seconds, which is past the line, what would the value of y be? Okay. This does represent 1 over the initial concentration. But I'm not going to take this and do anything to it because it just is what it is. Okay? Anybody else? Well, we're not going to leave out the 0 order. So here's our 0 order rate law. And again, the rate is still the same. So it follows that the negative change in concentration of A over the change in time is equal to the rate constant. And so that would be the differential equation, and the integrated equation is this. So that's a lot simpler, isn't it? So for a 0 order reaction, if we graph concentration versus time, it's linear. And that's because the reaction rate doesn't change as the concentration changes. With the first and second order, as the concentration gets lower, the rate gets lower, and so this type of a graph is not a straight line. Here the slope is equal to the negative of the rate constant. So any questions about that one? Book didn't give any examples. It's the same idea. So if you had an actual graph and they said, well, what's the concentration at this time? You'd plug that time in here with the rate constant and, well, from the equation, and y would be equal to the concentration. Yeah, it's even simpler. So, yeah, it's like we did the hard one, so we don't even need to mess with this.
So if you gave us a graph of that, and both first order and the zero order are aligned with negative slope, how do we calculate it?
The difference, that's a good question. So this is a straight line with a negative slope. And the first order was also a straight line with a negative slope. How would we tell the difference? You'd know the difference because of the label on the y-axis. So this is graphing the natural log of the concentration. The zero order is just the concentration. Excellent question.
So just to clarify for the test, memorize these.
I think you should memorize these things that I wrote on the whiteboard, yeah. The rate laws. And we're actually, at the end of today's lecture, there's a nice summary slide from your book. Okay, so half-life. You should have heard of half-life. Usually you think of this in terms of radioactivity, right? Half-life is the time needed for a sample to decay to half of what it was to start with. It's the time to 1/2, right? We can also apply this to a reaction. It's the time needed for the concentration of the reactant to fall to 1/2 of its initial value. So same concept. So just a little what if. If the concentration is 0.5 molar to start with, and the half-life is 50 seconds, what would the concentration be after 50 seconds? Half of it, right? Yeah, this is not supposed to be a trick question. So it would be half of that, 0.50 molar divided by 2. Okay? 0.25 molar. That's the concentration after 50 seconds. What about after 100 seconds? 0.125. You divide it in half again. So every 50 seconds, every half-life, you cut it in half. So then we take the 0.25 and divide by 2, and we end up with 0.125 molar. Okay? That's just the concept of half-life. So the half-life expression in terms of how it relates is different for different reaction orders, of course. So for the first order reaction, this was the integrated rate law. So I'm showing you the other version, not this is the equation of a line form, but just this one. So how can we figure out what the equation for the half-life is? Well, we say, well, T is equal to T1/2. So at T1/2, what happens? We know that the concentration at that time is half of the initial concentration. So we can put these into that expression and do something. So the natural log, we've got A at time t. Well, the concentration of A at time t at the half-life is 1/2 of A0. And then divided by A0. And that equals negative K, and here T is the half-life. Well, what happens over here? This is natural logarithm of the whole thing. The A0s cancel out, don't they? And so negative K T1/2 is equal to the natural log of 0.5. Yeah, yeah.
We had the same kind of a rate constant. It was just
Yep, it's very similar to what happens with radioactivity. So the natural log of 0.5 is negative 0.693. So negative 0.693 is equal to negative k times t1/2. Okay, perfect. So what does t1/2 equal? t1/2 equals 0.693 divided by the rate constant. The half-life here depends only on the rate constant. It does not depend on the starting concentration. And so that would be true for radioactivity. Any questions? So T1/2 is 0.693 over K. So if we graph the concentration versus time, we get a curve like this. Here at time 0, the concentration at 1, after one half-life, it drops to 0.5. After another, it drops to 0.25. Every half-life, the concentration gets cut in half. Yeah, this will be true for every first-order reaction. The half-life will be equal to the rate constant divided by, 0.693 divided by the rate constant. Okay, a first-order reaction has a half-life of 26.4 seconds. That seems like it might be important, so I'm going to write that down. T1/2 equals 26.4 seconds. How long does it take for the concentration of the reactant in the reaction to fall to 1/8 of its initial value? So there are mathematical ways to do this, but you can also do it just very simply. So if we start at 1 and we go to 1/2, and then we cut that in half, we go to 1/4, and then we cut that in half, we go to 1/8, right? And this is what the question is asking for. How many half-lives does it take to get there? 3. 1, 2, 3. So that would be 3 times the half-life. 3 times 26.4 seconds. $79.2. That seemed too easy compared to that other stuff. Like, wait a minute. There are some things that are just very straightforward, and then other things not so much. For the second order, here's our integrated rate law. And to figure out what the expression for the half-life is, we're going to do the same thing. We're going to take that at the half-life, the concentration is equal to 1/2 of the initial concentration. So I'm just plugging these things into that equation. This is kind of ugly looking. What is that equivalent to? We've got a fraction in the denominator. So we can bring that to the top by just inverting it, right? So that's the same as 2 over A0. And I'm trying to get T1/2 by itself, so I'm going to subtract 1 over A0 from both sides. I'm going to try this again because it's too messy. That's a 2 over A0. So I'm going to subtract 1 over A0. And that's going to equal KT. T1 half. Well, 2 over A0 minus 1 over A0 is just 1 over A0. So T1 half equals 1 over K times A0.
So now it does depend. The half-life does depend on the concentration.
Yes, for second order reaction, the half-life depends on what the initial concentration was. So there it is, typed out nice and neat. So for second order reaction, half-life depends on the initial concentration. If you have a low initial concentration, the half-life will be longer because it's in the denominator. So the smaller this is, the longer the half-life is. For zero order, here's our integrated rate law, and we can plug these things in again. So we've got 1/2 A0 is equal to negative K T1 half plus A0. Here I'm gonna subtract this one from both sides to move it over here. There's different ways to rearrange these. K T1 half is going to equal to A0 minus 1/2 A0. So that is equal to 1/2 A0. And then we need to get rid of the K from the other side. So the half-life is equal to the initial concentration divided by 2 times the rate constant. So there it is. For zero order reaction, the half-life also depends on the initial concentration, but the dependence is different. Here the half-life gets shorter as the concentration increases instead of getting longer. Any questions? I would recommend memorizing this stuff. And a good way to do that is to make some flashcards. If you're not already using flashcards, I think you should start. Carry them around in your pocket. You'd be amazed at how many little bits of time you can find to just keep these things fresh in your brain or to memorize them in the first place.